Hey, what's up, guys? Okay, so in this video, since we previously talked about the algebra, the skin, right? So we know that the skin, and we talk about like there's an idea called the solid for a ring space. We can define a f the OX module, right? So we can define a sheaf f, right? So called the OX module. Say f, I call OX module. Okay. So F call is module, right? So basically means that as we say that so basically if you take the FU and the FV and such that and the U V, so this is a definition. So F is a sheaf, and for each, and there's always module structure. So we have this. This is the restriction such that this diagram commute. This diagram commute. This should be yeah. This is U. This is V. Okay, and so it's natural to ask. So the natural question that obviously need to ask is that what is the FU F module, or what kind of, maybe you how to construct some F, or how to construct OS module when X is affine. Okay, so obviously the answer will be very simple. The answer is that you can just take the, let's say X is a affine, let's say spec of R. Then one can just take M to be the R module. Okay, so which we want to construct. So our goal is to our goal is that somebody given you M, which is R module, and then we want to construct M tilde, which is the OX sheaf, or the sheaf of module on a affine scheme, right, on this X. Okay. Okay, so before we do this, so this is our final goal. Yeah. So in this video, let's first quickly recall the localization of module. Okay. So the first one, let's first quickly recall localization of ring. I think previously I say something. So like somebody gives you R, right, and then you take S, which is subset, and S is multiplicative. So basically means that 1 belongs to S. If A, B belongs to S, then A times B belongs to S. Okay, and S inverse R is a set which R divided by S, where R just belongs to R, small s belongs to S. And the addition just very simple. You just define R1 divided by S1, R2 divided by S2, just S1 S2, R1 S2 plus S1 R2. Okay, and R1 S1 times R2 S2 will be R1 R2 S1 S2. And I also need to define an equivalent relation such that if R1 S1 equals to R2 S2, basically there is a S. Maybe I use T belongs to S, such that there is annihilation by T. Okay, so this is the standard one. And I think in some video that I also proved that the prime ideal between the prime ideal of localization ring. Okay, so there's some correspondence. And also in the affine scheme, right? Each point is a prime ideal, so each stock is AP, and you can define a distinguished open set. And we know that the spec of the localization AF is isomorphic to the distinguished open set NF. Okay, so our generalization is obviously simple, right? Our generalization is that we just define the localization of ring to localization to the module. Okay, so R settings are its commutative ring with identity, and then S is also a subset of R. And then let's say M be a R module. Okay, so we can S define, we write S inverse M. This guy is also R module. So set to be M divided by S, where M divided by M belongs to M and S belongs to S. Okay, and the same thing, right? If M divided by S is the same as N divided by T, there exists the U belongs to S, such that MT minus NS U is 0. Okay, and addition. addition is defined to be n, let's say m divided by s plus n divided by t is defined to be the standard one. And also rs mt multiplication will just be simple multiplication. Okay, and okay, and the R module structure is simple, right? So R module structure is that if I want to say R times n divided by s, then I just define R n divided by s. Okay, because it's R module, and basically there's a map. Right, so this guy just extended to here. Okay. Another definition, which is if you know the tensor products, that one can define this to be the S inverse R, right? Tensor product with M over R. Let's say this is you can view this is R divided by S, right? And M. Okay, so basically you need to view S inverse R as R module. Okay, and since it's tensor product, right? So you can translate the coefficient, translate scalar, right? So yeah, you can check. You can check this is true. Yeah, I just leave you to check. Okay, leave you to check these two are equivalent. Okay, and yeah, this is just some standard notation. Okay, so okay, so the rest of the video that we need to prove important property, basically localization. So these are famous results, and this one is where we will keep using. So localization is exact. So so everyone knows about the module exact sequence, right? So if let's say, so one can define the ABC, right? So one can define ABC to be exact, just the image the same as kernel, and as a module homomorphism. Okay, so the theorem says that if you have ABC which is exact, and you take S, so okay, so ABC are all R module, and you take S to be the multiplication set of R, then S inverse A, S inverse B, S inverse C is exact. So if this guy is exact, then this guy will be exact. Okay. Okay, so before we do this, let me just quickly say something maybe you don't understand. So if you have module homomorphism U from A to B, then there's an extension map from that's called U tilde, and a very simple, that's A divided by S, right? A divided by S, I just define to be U tilde A divided by S. Also, right, just define to be U of A, right? Because U of A in B divided by S. So obviously this is you can check this is consistent definition. Okay, so right, so this is the goal we need to prove. Okay, so this proof is very simple. Okay, so obviously so we need to show that okay, the proof, right? So we need to show that the image of U tilde is the same as kernel V tilde, right? And provided the image of U is the same as kernel V. Okay, so obviously that it's easy to check, right? Because you got VU equal to 0, right? So this means that if you do this, it's obvious that V tilde U tilde is 0. So we always have image of U tilde as a subset of kernel V tilde. So one direction is trivial, right? Because you just check VU, right? Account A divided by S, then you get 0. Okay. Obvious, right? Because this will become a VUA divided by S, which is 0. So VUA. Okay. Okay, so let's prove the next directions. So the next directions we need to show that the kernel V tilde is in the image of U tilde. Okay. So let's maybe I take the B divided by S, and such that V tilde B divided by S is 0. So this means that we have V of B divided by S is 0. So right, so this guy is in this, right? So there's a T belongs to S, right? Such that V of B T V of B 0 is the same as V of TB. Why? Because V is a module homomorphism. So VTB. but then we know that right. So now TB is here, right? So TB V is 0. So that means it is the A belongs to A, such that U of A is VTB. Oh, sorry, it's TB. Okay. So obviously that you can, if you take U tilde X on A divided by, right, we need to write B divided by S, right? So ST will equals to U of A TS B divided by S. Okay, so we prove that A divided by ST in the A divided by ST here will map to B divided by S, which prove that if you take any guy which B divided by S such that this guy is 0, then it always come from left. Okay. Okay, so yeah. So let me just quickly tell you the results of how to associate it. So basically this is called associated affine scheme. So associated module, right? Module to affine scheme. Okay, so we need to, in order to, so it's very simple, right? We start from spec A and O spec A, and then let's say M is a module. And we need to, obviously that in order to give a sheaf, we need to specify the stops, right? So yeah, one definition is that we say, well, what is the stops, right? So let's say F, right? So let's say, so usually use M tilde. Okay, so M tilde is a sheaf, and it's on it's stocks, right? Stocks at P, prime ideal P, we'll just define to be the sheaf, like the localization of prime ideal P of this M. Okay, so this is the definition. Okay, so you specify all the stocks, and then you know that what the sheaf is completely determined by the stocks. Okay, so this is the definition. Okay, so the next video that we will play around with this definition, and I think maybe it's time to talk about a coherent sheaf, quasi-coherent, that kind of terminology. Okay, but in this video, that's just starting points to give you this localization is actually very important, that we will keep using it. So this is why we need to say something. Okay, so that's it. See you guys next videos.